When you're using samples, you have to account for the fact that different samples give you different results. Each sample is likely to be different, so although you're calculating the same statistic on each sample, you're likely to get different results. You have to consider how different the statistic could be under different samples. The sampling distribution summarizes all the possible values that you could get under different samples, and how likely you would get each value. You can present the sampling distribution as a table, where x is the possible value and px is the probability of getting the value. Or you can present the sampling distribution as a graph, where x is on the x-axis and px is on the y-axis. The focus of this topic is to identify what the sampling distribution looks like. What the sampling distribution looks like depends on what you're measuring. Let's turn to the sampling distribution of the mean. This is our guiding example. You want to estimate the average weight of puppies in the population. You randomly pick 3 puppies, weigh them, and calculate the average. If you pick 3 different puppies, you get 3 different weights and a different average. Different samples give different results. There's a sampling distribution of possible sample means. Let's work out what the mean and standard deviation of the sampling distribution would be. Let's say the probability distribution of the weight of all puppies in the population has a mean, mu, of 15 pounds and a standard deviation, sigma, of 2 pounds. You pick 1 puppy from the population. That is, you draw a sample of 1. You don't know which puppy you'll get or what its weight is, so the weight of that puppy is a random variable. What do you think the probability distribution of that weight is? The possible weights for that puppy are just the possible weights of all puppies in the population. So it's the same as the probability distribution for the population. The expectation of x is the same as the population mean, mu, of 15. The variance of x is the same as the population variance, sigma squared, so 2 squared, of 4. The standard deviation of x is the same as the population standard deviation, sigma, of 2. If you're drawing a sample of 1, the sampling distribution just duplicates the population probability distribution. What if you pick 3 puppies instead? What would then be the expected value and variance of the sampling distribution? The weight of each puppy is a random variable, so the sample consists of 3 random variables, x1, x2, and x3. The sample mean is the mean of 3 random variables. It's a linear combination of random variables. So you can use the rules for calculating the expected value and variance of linear combinations of random variables. Each random variable has the same probability distribution, and they're all identical to the population probability distribution. It's as if the xi's are independent copies of the same master distribution, x. The expectation of x bar is the same as the expectation of x1 plus x2 plus x3 divided by 3. The 3 is a constant, so it can be taken out of the expectation. The expectation of the sum of 3 random variables is the same as the sum of the expectation of each random variable. The expected value of each random variable is 15, so the total is 3 times 15. The 3 and 1 on 3 cancel out, so you're left with 15. The expected value of the sampling distribution is 15. The variance of x bar is the same as the variance of x1 plus x2 plus x3 divided by 3. The 3 is a constant, so it can be taken out of the variance. When it is, it's squared. The variance of the sum of 3 random variables is the same as the sum of the variance of each random variable. The variance of each random variable is 2 squared. The 3 and 1 of the 1 on 3 cancel out, so you're left with 4 on 3. The standard deviation is the square root of the variance, so 2 on root 3. So if you're drawing a larger sample and averaging the values, it doesn't change the expected value of the sampling distribution, but it does narrow the standard deviation from 2 to 2 on root 3. Interesting. What if you keep increasing the sample size? We want a general result that's gonna work for any situation. For any random sample of size n from a population with any mean mu and any standard deviation sigma, think of the symbols as placeholders for numbers. The sample mean is x1 plus x2 plus all the x's up to xn divided by n. The expectation of x bar is the same as the expectation of x1 plus x2 plus all the x's up to xn divided by n. N is a constant, so it can be taken out of the expectation. The expectation of the sum of n random variables is the same as the sum of the expectation of each random variable. The expected value of each random variable is mu, so the total is n times mu. The n and 1 on n cancel out, so you're left with mu. The expected value of the sampling distribution is mu. The variance of x bar is the same as the variance of x1 plus x2 plus all x's up to xn divided by n. The n is a constant, so it can be taken out of the variance. When it is, it's squared. The variance of the sum of n random variables is the same as the sum of the variance of each random variable. The variance of each random variable is sigma squared. The n and 1 of the 1 on n cancel out, so you're left with sigma squared on n. The standard deviation is the square root of the variance, so sigma on root n. The formulas show that the sampling distribution of the sample mean will always have a mean equal to the population mean, and a standard deviation equal to the population standard deviation divided by the square root of the sample size. By the way, congratulations. You just did a math proof. Not so scary, was it? The formula tells you the standard deviation of the sampling distribution, provided you know the standard deviation of the population. The problem is you can't see the population, otherwise you wouldn't be using samples. So you have these wonderful formulas, but you can't use them. Or maybe you can. You can use the sample standard deviation to estimate the population standard deviation. When you do this, the standard deviation of the sampling distribution is called the standard error of the mean. The standard error estimates the standard deviation of the sample mean. See our statistics in Excel course on how to generate a sampling distribution and calculate its properties using Excel. We've figured out the expected value, variance, standard deviation, and standard error of the sampling distribution of the sample mean. Now we want to know its shape. Fortunately, there's the central limit theorem, CLT. The CLT tells us, as long as all your observations are independent, so you pick a random sample, and you're observing the same thing, so they all come from the same probability distribution, making the random variables IID, then the sampling distribution of the sample mean is going to look more and more like a normal distribution as your sample size increases. It's called limit because the sample size is increasing. Let's look at the CLT in action. Here's a normal distribution. We could simulate drawing random samples from it. We ask the computer to draw 10,000 observations. This is the sampling distribution for a sample size of 1. What if we draw 2 observations at a time and average them? This is the sampling distribution for a sample size of 2. Let's average 5 observations. 10 observations. 100 observations. You can see that the sampling distribution of a normally distributed variable is normally distributed. We can imagine at this stage you're not too impressed. Let's consider a random variable that follows a uniform distribution between 0 and 1. We ask the computer to draw a random sample of 10,000 observations. This is the sampling distribution for a sample size of 1. What if we draw 2 observations at a time and average them? This is the sampling distribution for a sample size of 2. For the average to be close to 0 or 1, both observations need to be close to 0 or 1, which is unlikely. You're more likely to get a mix of high and low values, so you end up with a little mountain in the middle. Let's average 5 observations. 10 observations. 100 observations. We started from a random variable that's uniformly distributed. We average and average and average, and eventually we get something normal. It's already close to normal once we reach 10 observations, which isn't hard to get in practice. Let's test the CLT on something really skewed. As skewed as you can think of. A chi-squared distribution with 1 degree of freedom. We ask the computer to draw 10,000 observations. This is the sampling distribution for a sample size of 1. What if we draw 2 observations at a time and average them? This is the sampling distribution for a sample size of 2. Let's average 5 observations. 10 observations. It's still very skewed and doesn't look normal. Because of the initial shape, we're gonna get a lot of values close to 0, but we'll still get some values slightly bigger and that'll compensate. Let's average 100 observations. Although we started from something that really doesn't look normal, provided you average enough values, the sampling distribution becomes normal. Isn't that amazing? How large does the sample size need to be for the sampling distribution to be approximately normal? You may have heard of rules of thumb like at least 30 observations, but it actually depends on the population distribution. The more non-normal it is, the larger the sample you need. If you're drawing from a normal distribution, we saw that the sampling distribution already looked normal when we were averaging only about 5 observations. When we were drawing from a uniform distribution, we needed about 10 observations. Whereas when we were drawing from a chi-squared distribution, we have to average about 100 observations. Overall, if the population probability distribution is normal, then the sampling distribution of the mean is normal. If the population probability distribution is not normal but the sample is large, then the sampling distribution of the mean is still normal because of the central limit theorem. If the population probability distribution is not normal and the sample is small, then you're stuffed. For more lessons on statistics, visit alphas&betas.org.